This is project 25073, improving energy efficiency in semiconductor HVAC systems. From left to right, I'm Isaiah Hernandez.
I'm Ivan Hernandez.
I'm Nick Patton.
And I'm Addie Secker-Martinez.
So clean rooms are essential to the manufacturing of semiconductors, and most of the manufacturing processes that take place require strict control when it comes to particulate matter, temperature, and relative humidity. This is really because semiconductors are very sensitive to contamination, and even a single particle could potentially cause quality issues with the device. So these clean rooms are classified by international standards, and they define the allowable number of particles in the clean room and the required number of air changes per hour. An air change occurs when the volume of the air in the clean room is entirely replaced. So more air changes allows for better contamination control. The HVAC systems used to meet these standards and requirements account for around 50% of the total energy consumed in a fab. To further put this into perspective, a single fabrication facility can use as much energy as 50,000 homes. And as the semiconductor industry continues to grow exponentially, and with governmental funding like the CHIPS Act, the HVAC systems also need to advance to help protect the environment. So the goal of this project is to optimize an HVAC system to achieve the lowest energy cost. We as a team have designed 4 theoretical HVAC systems that we call exhibits A through D, and these exhibits allow us to accurately compare these models and determine the most cost-effective system. Exhibit D was found to have the best performance and lowest cost with an NPV of negative $21,705,000, and Exhibit A acted as our control with no optimizations, and it resulted in a net present value of negative $153,474,000.
For our project, we created 4 exhibits with different airflow configurations to explore how semiconductor manufacturers can reduce energy usage and operational costs. Exhibits A, B, C, and D each present a different combination of return and recycled air layouts for comparison. In Exhibit A, each cleanroom operates independently with 1 inlet and 1 outlet. Since there is no use of return or recycled air, all incoming air must be treated from its original outside condition, resulting in higher energy consumption. In Exhibit B, the outlet air from Cleanroom 1 is sent to Cleanroom 2, and the outlet from Cleanroom 2 is sent to Cleanroom 3. Each cleanroom transfers only the necessary amount of air to the next, and any excess air is exhausted. This approach reuses some of the conditioned air, helping to reduce energy usage. Exhibit C introduces air recycling while keeping the cleanrooms independent. The outlet air from each cleanroom is partially recycled and mixed with fresh outside air to help bring the temperature closer to the desired value. With an exhaust to recycle ratio of approximately 0.2, around 83% of the outlet air is reused, significantly reducing the need for conditioning fresh air. Exhibit D combines both cascading and recycled air systems. Like Exhibit B, each cleanroom sends only the required air to the next one, but the excess air is sent back to Cleanroom 1 and mixed with incoming fresh air. In Cleanroom 3, the ratio of exhaust to recycled air is 2:1. Using MATLAB and Excel, we modeled a basic HVAC system that simulates air treatment in a controlled environment. Air first passes through a pre-filter that removes particles 0.3 micrometers or larger. It is then humidified or dehumidified based on the outside air's relative humidity. Next, the air is sent through a thin fan heat exchanger with heating and cooling coils to reach the target temperature. Once conditioned, it passes through a fan filter unit and a HEPA filter to ensure particle removal.
The economic analysis of our design project evaluated the financial feasibility of 4 system designs, exhibits A through D, using cash flow diagrams. These diagrams incorporate capital costs, annual maintenance, and utility expenses such as electricity, distilled water, and others, in addition to equipment depreciation based on a project lifetime of 12 years. A net present value analysis was done on each exhibit using a minimum acceptable return rate aligned with inflation according to the U.S. Department of Treasury. An IRR analysis was deemed impossible, as with no income, our calculated IRR would be infinite. The NPV analysis identified Exhibit D as the most cost-efficient option with the lowest financial loss, with an NPV of negative $21 million. At the same time, Exhibit A demonstrated the highest financial loss with an NPV of negative $153 million. These cost efficiencies were expected based on Exhibit D being the most optimized air system. The high yearly utility costs from each exhibit were the largest cost by a large margin, which meant that the other ancillary costs, such as capital costs, had much smaller impacts on the resulting NPV. In this table, the 2023 utility costs were broken down by utility type and unit op. As you can see in Exhibit A, B, and C, the steam humidifier made up over 50% of the utility costs, the main driver being the high energy and distilled water costs needed for humidification. In Exhibit D, the heating and cooling took up the majority of the utility usage, with over 52% of Exhibit D utility costs coming from that operation. Our calculated costs for each exhibit may not be completely accurate, but they serve their purpose as a form of comparison between the exhibits to see which is the most feasible and efficient. Our overall results point to Exhibit D being the most cost-efficient option, with the lowest NPV of negative $21.7 million after a 12-year period.
In addition to optimizing airflow for cleanroom standards, we also considered several broader impacts, especially those tied to cost and sustainability. Starting with HEPA filtration, while HEPA filters are highly effective at removing particulates, they do not address odors or low-level chemical vapors. Over time, these can accumulate in the air. To mitigate this, we recommend scheduled air replacement every few days or weeks, which not only improves air freshness, but may also extend filter life. This helps reduce operational costs tied to frequent filter replacement. Water usage is another concern, especially in Phoenix, where water scarcity is a serious issue. Cleanroom HVAC systems that rely on evaporative cooling or humidification can put added strain on local supplies. By shifting towards closed-loop or water-efficient cooling systems, we can reduce both environmental impact and long-term utility costs. Energy consumption also plays a major role. Cleanrooms require constant airflow, which leads to high electricity use. By incorporating variable speed fans, energy recovery systems, and smarter airflow routing, we can significantly lower energy demand and operating expenses. Lastly, to maintain system reliability, we suggest sensor-based monitoring to detect early signs of airflow disruption or filter clogging. This predictive maintenance approach helps prevent costly downtime and keeps performance consistent. Overall, the proposed model of Exhibit D, especially with these enhancements, offers a balance between cleanroom performance, operational efficiency, and sustainability.